Hey guys, it's Jonathan Nathan here. I'm going to do the ECON3123 Organizational Economics oral presentation. And so that requires us to look at question 2 from the first problem set. And specifically, it wants us to look at question parts A and B. So let's get those nice and highlighted. There you go. So this kind of problem is it's a kind of a typical agent principle problem. So let's get some nice colors going. So I want to put we got principal, and it's easy to think of him as kind of like a manager or an owner. He's kind of got this profession, and what he wants output, so he can sell this output. And then you have your agent, which is kind of easier to think of as an employee or worker. So the principal, he wants the agent to give him output, and that kind of makes him happy because he can sell it, he can get more money, and that kind of increases general utility, is happiness. But however, there is one kind of problem with that, is that the agent will not work for free. He wants something else by himself. He wants a wage. So he also wants a bit of money for all the effort, the kind of output he produces for the principal. So it's easy to kind of think of this as a kind of as a macro framework. So that will kind of come into play later on when we're looking at maximizing alpha, or this kind of a lump sum payoff thingy-majig. But we'll get to that later on. So we got our maximum macro framework. So the principal, he wants to produce, he wants output so he can sell it. The agent wants a wage for the output. So yeah. So now let's kind of set up, look at the question and set up a model. So let's go through. So I'm going to use that nice kind of green. In this problem, we will consider a multitasking problem where the principal can only incentivize the agent on one task. So there we've got our first kind of tips of what we're kind of dealing with. So there's going to be a multitasking. Oh, that's awful. Give me just a sec. I have no idea why it's doing this. We'll only incentivize the agent on one task, but there will be a crowding in effect. So not only is it kind of a multitasking, I'm going to use a proper highlighter. So multitasking. No, so it's just saying not to work at all. That's right, because it's not recognizing as text. No, I'm just going to go back to. There you go. I do apologize. I've been having issues with this Surface Pro 4 for a while now, so just gonna have to kind of work with them for now. So yeah, so we got a multitasking model can only affect the principal can only incentivize the agent on one task, but where there is a crowding in effect. So you got some nice kind of dynamics going on over there between the efforts. Able to put on and kind of how he weights whichever he chooses. So yeah, effort agents will do. Yep. So the agent's effort in one task reduces the agent's marginal cost of effort in the other task. So this doesn't really mean a lot to us until we kind of start building the mathematical model. So let's come back to this. Let's got that one there. Okay, cool. So let's build a model. Here's a great joke for the meantime. Here we go. Why do economists do it with models? Well, I hear you say, I don't know. Well, we can say, because there is no shortage of not the of demand. Oh, this is going sideways on me. Demand. There's no shortage of demand for the curves. They supply. Yeah, just for one of you kind of looking for some econ jokes, that's a great one there. And that can all be attributed to the wonderful Rhea. Shout out. Yeah, okay. Anyway, back to the more important things in life. I don't know. I suppose that's kind of arguable. Come now. Just love it when technology just decides to have a shit on you. Cool. Well, that didn't work. Go to plan B. Oh my word. So let's go in reverse. There we go. Okay, that got remote. Done. Okay, so back to the problem at hand. We've got utility, so let's go through it. So there are two tasks, task 1 and task 2. So task 1 and task 2. So I think this is where that second part comes in really interesting. Task 1, task 2. So task 1. Nah, let's kind of go in order. Got task 1 and task 2. So the principal wants, or the agent can do task 1 and can do task 2. And as it says here, the principal benefits from the agent's effort in both tasks. So I think kind of in this one it's a little bit misdeceiving when you actually look at it in detail. So let's write down that. So that's the principal is utility equals output 1 plus output 2 minus W. I suppose you can think of it as task, but I find it a lot more easier to think of it as output. So say, so essentially the way I kind of think about it is the agent, he can kind of make things, like he grabs a hammer, does his task, and then he produces output. Well, you know, if you're in a service industry, I suppose it's a bit more relevant where his task could be, you know, waiting food or picking up calls at a call center. You know, they directly benefit the manager there. So I suppose you could, but for me, I prefer to think of it as output. So I'm gonna just kind of run with it going output. So you got output 1, and it doesn't actually change or have any kind of implications for this model. So yeah, I'm gonna run with output. So output 1 and 2, and then we've got our wage. So as you can see from the utility model here for the principal, he enjoys output. Output is really beneficial. Output is positive. So as we said before, kind of in that macro kind of framework, output is really good for him, makes it better. He can then sell his output or benefits to customers, and they pay him for that. So yeah, as you can see, it's kind of got those plus signs in front of it. So they increase his utility, and he benefits from both of them, not just one of them, and in equal measures as well. So I think those are kind of key factors to keep in mind. And then we get to like the second term here. So this W here. So he can sell the output, but then he has to kind of coerce the agents into producing the task or the output. And to do that, he needs to supply a wage. But he doesn't like that, because that means the wage is monetary, which means so it has to come out of his pocket. So he doesn't like that. That's money that could be going kind of in his pocket, but no, it has to kind of go to the agent. So we're gonna quickly write down here wage is negative. So he doesn't like it. Now let's go to the second part of the question. Let's continue with this question up here. The principal benefits agent. So where x1 is. Okay, cool. So then we got effort in x1, effort in x2, got that one down as well. So what we're saying here is x1 equals e1. So essentially our output in task 1 is directly related to the effort put into it. So what happens here is that, well, and x2 equals e2. So it's a similar case for both of them. Come now. So yeah, what we can kind of say here is that the agent puts in effort and he produces output. So what we're saying is that there's a direct linear relationship between the two. So if an agent puts in, say, 1 effort, whatever that may be, he'll get 1 output in return. So it's not like he puts in triple the amount of effort, he gets 6 times the output back. No. It's just 1 effort, 1 output, and it's the same case for the for effort in task 2. Whatever he puts in, he gets out in output. So yeah, I think that's also quite interesting to look at. And now let's look at the agent's payoff function. So these are all kind of payoff functions, utility functions. So so UA equals W minus half of E1 squared plus E2 squared. So this multitasking problem is kind of encapsulated in these kind of output functions here. So I've got x1 and x2, and you've got these two kind of efforts at e1 and e2. But the second part of the question is it incorporates this crowding in effect. We can see that in the form of e1 and e2 squared. So what we're saying here is where it gets quite interesting, at least on the agent side anyway, is that wages make him happy. So he really enjoys it. He loves that. And then he doesn't like effort. So you can see this negative sign here goes straight onto those two. And yeah, he doesn't like that. It makes him sad. E1, E2 is negative. He'll prefer to, I don't know, enjoy the wage and not have to do anything to get it. That would be kind of living the dream, I suppose. I'll at you, was it not non-labor based income? Yeah, that's kind of living the dream, getting paid for doing jack shit. Excuse my language, but that's kind of what we want in life. But unfortunately, that's not the case in our model. So, as we'll see later, kind of wages are based on output. So, limiting ourselves to kind of the case. But yeah, this second term here, this this crowding in effect is actually quite interesting, because over here it's negative, sure. So at first it looks like it's going to harm the agent, but however, once you kind of apply this negative half, that turns into a positive. So you're thinking like, wait, what? That doesn't make sense. But we said he just likes, sitting on the beach and doing nothing, getting paid for nothing. But as it turns out, in this model, if he puts effort into one task, he actually gains utility in the other task. Like, doing the other task makes him a little bit more happy. I'm trying to think of a real world kind of example here, but it's really kind of coming to. I suppose one thing quite relevant to us is doing mathematics and economics. Go figure, right? Exactly what we're doing right here. Is that doing mathematics builds these fundamental mathematical skills, but then they're really easily transmuted into the study of economics. As you can see, there's quite a bit of mathematics, and it makes the actual study of economics a lot more enjoyable. Whereas other people who aren't doing mathematics and don't have this kind of crowding in effect, can find the study of economics quite hard and daunting and quite not fun. It decreases their utility. But in our case, the agent doing task 1 makes task 2 more fun or more better for him. So he gets like I don't want to say intrinsic benefit, but he gets benefit from doing the second task, doing the first task. So yeah, so wage makes him happy. Effort doesn't. The effort doesn't really make him happy, but it kind of does. Well, effort in one task doesn't make him happy. Effort in one task and then in the second task makes him a little bit more kind of happy. Like, it's not a one-to-one kind of relationship there. Anyway, okay, cool. So we've done that. Now let's look at the wage, because that gets pretty important. So let's put a little comma in there. So our wages equal the form of alpha plus beta y. So let's just break that down. So alpha is a constant, so it's going to kind of be this like a lump sum payment, and this is quite clever on the side of the principal. We'll get to it. It's pretty sneaky what it can do with it. That being said, let me just fix up the alpha. It looks really awful. So yeah, so it's this kind of lump sum payment. You can think of it as like a base salary almost, or a charge, to use something to produce effort, or like I think one of the examples thrown around in class was cab drivers, cabbies, pay for the rental of the car for the day. They drive around, they do the output, and yeah, they pay to produce things. And then you've got this beta here. So beta here is kind of the incentive strength, how much the principal, because this beta and alpha are chosen by the principal, whereas effort is chosen by the agent. So we can see here the wage as a function, wage as a function of beta and alpha. So it's definitely chosen by the principal. And then the output, which is a function of E1 and E2, is chosen by the agent to give back to him. So you got all that. That's great. So you got this incentive strength. So how much is he going to increase the wage based on Y? So what is Y? Y is what did it say now? Y is x1. Okay, so that's where like the actual first part of the question comes in. So x1, so that's output 1. So what this is kind of saying to us is that the principal can only pay the agent based on the lump sum, the incentive strength, and the incentive strength multiplied to the first output. So he can only see how much the first output is. He can only give you money based on how much on the first output. However, what's really interesting is that he actually gets benefit from both of the outputs. But having this wage here, and over here, it shows that he can only provide benefits to the agent based on the first output. So you got a little bit of interplay here, which will be quite important later on. So yeah, and then what is output? That's on the effort. So how much effort the agent puts in. So let's all put this together. So much effort the agent puts into the first task is how much he'll get paid by beta, which results in a higher wage. But if he puts into effort 2, he does get bonus wage. It'll make the principal happy, as you can see over here, but you won't get paid for it. So it's how it is. So let's move kind of onto the actual solving of this model. Actually, we first need to kind of go to this next part of here, which is the timings. So 1. So let's go through. The principal offers the agent an incentive scheme. So he's gonna kind of think of it like, if you've had a job before, you kind of know how this will generally go. So the principal offers an interchange scheme. Says P says to A, or says to A, I'll pay you wage. I'll give you the money if you do the work for me. So he says, the principal goes to the agent. He says, I'll give you a wage of alpha plus beta y. And so think about it like you're there, you got a job, or you're at an interview, and then, the boss says to you, I'll pay you this wage, and then you got to think to yourself like, well, that's a good wage. So he thinks about it, and he thinks to himself, and he says, okay, I've just been offered this this wage W, but what else can I get? So he thinks about it. He thinks about W and his outside option. So that's a U of 0. So that's what he can get if he didn't choose the wage. What can he get? What's his next best offer? This is kind of a good example of opportunity cost. What's the next best thing I can do if I didn't accept the wage and have to work for you? That's U0. Okay. And then let's say you accept this wage. Say, that's a good wage. I accept that wage. Then you get wage. You get wage W. And now, based on this wage, you realize that you're gonna get this beta alpha plus beta y. Now you gotta choose up how much effort to put in. You gotta choose your effort for the two different. Now go away, stupid thing. So you gotta choose your effort for the two tasks. So what's kind of gonna maximize your utility? You gotta choose effort 1 and effort 2 in the two tasks, which makes you the happiest. So yeah, essentially. For then my favorite kind of past part, BBHMM. The skip can really be kind of skipped over for this model, so it's really not kind of what we're interested in per se for this question. But for the sake of kind of clarity, and it does have a lot of ramifications in more deep models. But BBHMM, bitch, better have my money. Thanks, Rihanna. Love it. Yeah. This implies that the agent, sorry, not the agent, the principal, support, pays the agent. So agent gets paid. I was saying, like, you can have richer models where, there might be the threat of, not getting paid. How does that implicate the agent's choice on what they're doing? Or, like, can they get, more? Or, I don't know. These are kind of things you gotta think of for richer models. But yeah, anyway, for now, it's a one-to-one. It's pretty simple. The agent does the work, he gets paid. Voila, done. Okay. So now what we're going to do is now I can get into like the question. Let's just first kind of math it. Yeah, we'll come to that one later. So now we can finally get into the question. So we get to A. I hear you saying like, wait, how do we get all that to A? So it's like for step 3. Wait, what? Step 3, I hear you say. So what we're going to do is we're going to solve this using backward induction. So we're going to work backwards. So in this kind of position, you want to kind of look at as the principal. You want to kind of position yourself as a principal. So you're the principal. You're going to offer a wage. Then the agent's going to think about it. Then if the agent accepts the wage, then he's going to choose effort 1 and effort 2, and then you're going to pay him. So the best way, you know, to kind of get the optimum kind of amount of money you can, is to work backwards. So you say, okay, I've just paid the agent, but I wonder what kind of effort he's going to put in it, because the amount of effort that I think he's going to put in it is how much I'm going to offer him. You know, can I get more effort out of it? Can I get less out of it? So, you know, we're going to work backwards. We're going to see what effort he chooses first, and then, you know, we'll make our move per se. So to do that, the agent gets wage W, and then he chooses his effort levels. So how is he going to do that? He's going to do that optimally. He's going to optimize. So that infers that the agent is going to maximize his effort in E12. Let me just write that down. He's going to maximize his effort, or let's put this in better. He's going to choose his effort 1 and effort 2 to optimize his utility. And what that's going to do is that it's going to maximize his utility. It's going to make him the most happy. So choose F1, F2. That makes him the happiest. So yeah, let's get to it. Yep. So what is he going to do? He's going to max utility subject to E1 and E2. So effort, and what is that equal to? That is W minus half E1 squared plus E2 squared minus, wasn't half there, it was E1, E2. Okay, cool. Yep. So let's break that down a bit. Let's kind of get it all together. And I'm going to say W, what does W equal to? W is equal to alpha plus beta y. No, sorry guys. Minus half E1 squared plus E2 squared minus E1, E2. Okay. So we got that. Let's break it down some more. Alpha plus beta. Just remember, y is equal to output 1. You can only measure output 1, which is equal to effort 1. So the agent can only get paid for his effort in the first task. So some of you can probably see where the agent is going to kind of land up going. So we're going to sub that in. E1 minus half E1 squared plus E2. I do apologize about this thing. It's been giving me grief for a while now. I'm not gonna lie, it is pretty hot on this tablet. Let's try raise it a little bit. Give it a bit of a break. Okay, so that's kind of the most we can kind of get it to. And so now back to that kind of maximization problem. So max alpha plus beta E1 minus, you know, I'm just gonna copy and paste this sucker. Minus, what's the point of, you know, having all this wonderful technology if you're never going to use it? There you go. Subject to E1 and E2. Oh man, this Surface Man is killing me. Okay, cool. So that's kind of where we're at. So in order to do that, we need to fuck it. And by fucking, I mean we need to take. Oh, this thing is killing me. Just give me a sec. Yeah. I suppose, you know, the benefits of, you know, copying and pasting, you know, a line, versus, you know, the problems of having to deal with issues of technology all the time. You know, choose your pick, right? Yeah, back to fucking it. So we're gonna take first order conditions. Wow, this is really not having it at the moment, is it? It's quite a shame. Let me just try one more kind of. Yeah, that should work a lot better. Okay, we got it on the kickstand now. Give it a little more air circulation. So what I want to do is kind of take the sorry, I'm trying to be a little bit sneaky. The partial derivative of UA. So remember, UA is this guy. This guy. Yeah, that's the one. Can I get that one there? And we'll take it to the first task. So that's E1. Oh my god, this thing's driving me mad. So E1 equals, okay, first derivative. So we got that one there, that's beta. So then we times out minus half. That's minus 2 over 2 E1. And then we got that other task. So that's half times minus. So that's plus half. That's plus half E2. Wow. That plus sign was amazing. Plus half E2. Oh my word. Would you look at that? And then, we do the kind of classic, serving for the critical points. E1 equal to 0. So that it implies kind of this whole thing is equal to 0. So let's solve that for kind of E1. So we got that beta there, that equals to 0. Oh, now it's really giving me grief, isn't it? There we go, much better. Equals 0. So kind of what we're getting is beta minus half E2. Come on, give me a 2 equals E1. So okay, it's kind of great. So we're just kind of in the process of fucking it. Cool, we got that. Then we'll do the same process for E2 because these are choices agents can make. So A over E2 equals. So we got no E1, E2's over there. But we've got one there, so we got a minus E2. So we're just using the power function rule here, and then plus half E1. So let's just tighten it up and up. And then again, we just kind of do the same thing. Derivative of UA, derivative of E2, set that equal to 0. E2 equals half E1. Fantastic. So what we're going to need to kind of do now is simultaneously solve these. So essentially just kind of subbing them in or minusing them up. But yeah, I kind of prefer doing, substitution in for this. So we're going to sub E2 equals. I do apologize for this. E2 equals E1 into. Oh, mate. Absolute grief. Yeah, and we're back. E2. Watch it still. Oh my god. So what we're going to do is we're just going to into E1. So that's going to kind of involve E1. Come now. I may actually just switch over to a pen quickly. So who knows where this is going to kind of get us into E1. So this is terrible. It's even worse. Okay, so we'll go back to E1 equals beta minus half brackets. So we got that E2 kind of going there equals that kind of half. Oh my word. Oh, what you all gone? Equals half E1. So equals what? Half E1 when they're all kind of at their peaks. How do you know this? How do you know that it's like an optimal? It's the best choice. Well, if we were to take the second derivative, oh my god, second derivative of this, you would get a negative e1, and you would get a negative e2 for the second one. So that implies that for the second order conditions, for them to have a negative value, it means that we have a peak. So kind of that's it. So I just kind of implicitly assume this. I kind of should have stated it a bit more kind of explicitly before. So yeah, so now we kind of got this all going. Let's kind of solve it for like optimal u1 equals beta minus a quarter e1. Okay, so take that over to the other side. Something feels a bit wrong. Sorry. It's a positive sign there, so that is a positive sign. Oh my god. So let's just change all of that. Oh my god. They drive me mad. Plus. I said plus. Okay, cool. So where we go is that. Now kind of solving for that. U1 1 minus 1 4 equals beta. So that gives us 3/4. E1 equals 4 over 3 beta. Now, given that, we now solve this into E2. So we've got E2 equals half 4 over 3 beta at the optimum. So what that kind of gives us is E2 equals 4 over 6 beta, which equals 2 over 3 beta. So there you go. So you got that E2 4 over 3. So as you can see, just comparing these two values, you can see that the agent is kind of going to prioritize this E1, whereas he's not going to put as much effort into E2 given beta. They've got beta in the same in either case. Yeah. So just looking kind of at the model and remembering what our wage is. Our wage was alpha plus beta y, which is really important, is that one. So alpha plus beta e1. Kind of remembering that, we can see that the agent really likes e1 because he's getting a lot of bonus of it from the wage. That's kind of his where he's getting the utility from. Whereas E2, it's actually fascinating that it's not a negative number. Why it's not the 0 or kind of nothing. That's kind of because of this this crowding in effect. He actually gets utility out of doing E2. So as he gets the utility out of the second task, not because he gets paid for it, but because he just generally enjoys it. So that kind of gives us that that 2/3 of beta. Because beta why you got that kind of beta there is because beta incentivizes E1. So the bigger the beta, the bigger the E1. The bigger the E1, the more kind of utility he gets out of that E2 term. Why? Because of that crowding in effect. So it's all quite dependent on that kind of on that beta term there. Beta influences E1, E1 influences E2. So hence E2 is a function of beta. Beta makes it happy as well. Let's just get kind of like another page going here. I'm going to need that one for the second, for part B. So yeah, so that's kind of where we're at right now. So let's go through and solve part B. So B is asking us for kind of beta star and alpha star are kind of optimal values of alpha and beta. Alpha and beta, and so these kind of are chosen by the principal. So yeah, that's quite, we've mentioned this before. But what we need to do is the principal now knows what the great alpha levels are. But this is kind of where it gets interesting. Is that you're not just solving for these alpha levels, but you also know that the agent. So let's say the agent's problem. So he wants to maximize beta and alpha subject to x1 utility plus x. This is properly up, where up is x1 plus x2 minus wage. They're part of things. I'm spending way too much time on this. Anyway, so that's the utility of the principal plus that. So all given E2 at E1 star E2. Come now. Oh my god. E2 star. So, but the interesting thing is that we can also incorporate the second step. And that was where the agent may accept or reject the offer from his outside alternative. So given the incentive structure of W, where W equals alpha plus beta E1, what this implies is that alpha allows the principal to kind of steal or kind of take away all the extra surplus that the agent derives. So what this can kind of do is it can ensure that the amount of utility that the agent gets will always be equal to his outside option. So anything he gets, above and beyond the outside option, if the agent does it properly, he can get it and kind of get it for himself. And so what this ensures for us is that UA, the agent's utility, will always equal U0 because of this alpha. We'll show how it's actually done later, but that's kind of has some implications for our problem right now. So what this implies is that we now have max beta, alpha of UP plus 0. And you're thinking, oh, hey, what's with the 0? Well, I do say, what's UA mod U0 equal to? 0. That's correct. So that means we're going to max UP plus UA minus U0. Okay, great. Oh, fantastic. So now, as we did before, let's break down this kind of this problem. So I'll say UP equals UA minus U0. So that equals I'm going to jump a couple of steps here. So that's E1 plus E2 minus W plus W minus W minus half. Yeah, may as well. I mean, done it once. May as well do it again. It just takes a little while to kind of get the sucker going. And of course, we'll do that. Come down. W. Okay, cool. Got it. Well done. Let's tidy this up. W minus half. That one, and then we got minus. Come now. Minus U0. Okay, there we go. There you go. So first thing you can kind of notice is those two are going to cancel. So then you got E1 plus E2. I think I'm going dyslexic here. E2 minus all of this minus half E1. Oh my god, this is awful. Just gonna duplicate that, shove that in there. Okay, there you go. That's kind of, let's just get rid of that last parenthesis there. That's it. That is what we're going to max. So this is now what we're going to max. There you go. So we're going to max that. So for beta and alpha. So what we got to do now is sub in those optimal values. So we're going to sub in E1 equals 4/3 beta, and E2 equals 2/3 beta. Is that correct? Yep, 2/3 beta. Okay, good. Let's just plug it all in. So we can plugging this in. 4/3 beta plus 2/3 beta equals 6/3 beta, which equals 2 beta. So we can just go straight into beta. Bam, straight up. What's really interesting here is, remember the alpha? The alpha got dropped in those two. This is the only place it kind of appeared. So we'll have to come back to that to find out what's kind of going on with it. So then we got, let's go, so 4/3 beta squared, that will equal 16/9. 9 beta squared, plus, then we got that 2/3, so that's 4/9 beta squared, minus 4/3 times 2, so that's minus 8/9 beta squared, minus U0. So, yeah, so let's just kind of punch this one through and kind of simplify it as much as we can. So, simplifying all of that, 16/420 minus 8, that's 12/9 beta squared minus U0. Minus U0. It seems to be a lot better when I don't put my hand on it, so let's try to keep my hands off it. Okay, 2 beta minus half. Minus half, that's good, but it's just over like minus 12/18. 12/18, that's, I'm just gonna put that through the calculator quickly. 12/18, so that's 2/3. So that's minus 2/3 beta squared. Beta squared minus U0. And voila! It's kind of as far as we're getting. So it's now, let's fuck it. So we take that U of P. Remember, U of P plus 0, so it includes that U of 8 term. And then we go for beta. What does that leave us? 2. So that comes down. Just double check. Yep, that's minus 2/2, 4/3 beta. Yep, that's kind of looks like where we're at. Let's just double check that. I've got a feeling that's not right. Give me 1 second. That's Yep, no, that's definitely correct. Well, not definitely correct, I could be wrong in my other source, but yeah, cool. Now let's solve that for beta. So, first thing we're going to do is very similar to last time. equals 0. Therefore beta equals 3 over 4 times 2 equals 6 over 4 equals 3 over 2. So that's going to be our beta choice. 3 over 2. That is going to be the best choice for beta for this principle, knowing that the effort, knowing that our agent is going to make his choice of effort. So yeah, that's kind of how he's going to give it. Now, this brings us back to kind of where it gets quite interesting. Is this alpha term? Alpha term. So we're going to solve this using something we kind of discovered, or I stated a little bit earlier, where there's this one, this UA minus U0, or not the UA minus U0, or UA equals U0. So in the question, it's stated that U0 equals 0. Let's go all the way back up there. He receives an outside option of 0. 0 equals 0. So, I apologize, it's really awful handwriting. U0, he says as he's making the mistakes, U0 equals 0. Okay, so now I go all the way back down to the bottom. We're going to say UA equals 0. This UA is going to be function of, E star 1, E 2 star, and beta star, and alpha. So that's going to allow us to solve for alpha, because we know all what's going on inside of it, and we know that it's equal to 0. So let's just kind of punch it out and kind of get it there. So wage minus kind of your effort cost function, E2 squared minus E1 E2 equals 0. So there you go. So that equals alpha plus beta y minus your kind of cost function again. Now let's do the G kind of just copy and paste. Yeah, why not? There we go. Okay, cool, done. Okay, if I could let go, that would be great. Anyway, cool. So that's done there. So now let's kind of break that down into all of our function of afterwards. So we got alpha plus, so let's go all the way back up. We didn't have that last time, so it's beta times E1, and E1 which was 4 over thirds. Beta minus, so what was it? We kind of go all the way back over here, look back up, and we kind of get that 2 beta on the one side. Then we got that minus 2/3 beta squared. Because that's at the optimals, we can just plug that one straight in, 2 over thirds beta squared. Beta squared. So there you go. That all equals 0. So kind of got alpha, and now we go over there, plus 4 over thirds beta squared minus 2 over thirds beta squared. That's definitely a 4 equals 0. Alpha equals 2 over 3 beta squared. So it doesn't equal, it's plus. Equals 0. And now we solved earlier for what the optimal value of beta will be. So let's just kind of sub that sucker in. Alpha plus 2 over 3. And we just got over there. 3 over 2 squared equals 0. So this is kind of what the profit the agent's going to kind of earn. So plus 4 over 3, so that's 4 over 3 times 9 over 4. Over 4 equals 0. So let's just cross multiply that out. 4 by 4, 16. 16 plus 3 over 9, 3 by 9, 27, 30, it's like 43. Let's just double check that. 4 by 4 plus 9 by 3, 43. There you go. All over 12 equals 0. So now alpha, as you can see, equals is 43 over 12. Let's see if that actually comes out to a nice number. 43 over. Unfortunately not. That's essentially what we've solved for questions A and B. But what gets really interesting is this alpha. As you can see, the agent or the principal chooses alpha that he steals, or essentially kind of captures all of the agent's effort, or the extra effort, all the extra kind of surplus, extra utility he would have gotten from, having that 4/3 beta squared, is just kind of captured by the principal, so ensures that he gets the most value out of the exchange. This also kind of allows us to ensure that that UA equals U0 part. So yeah, thanks guys, and I hope you have a good afternoon, and yeah, thanks for watching.